Buenos dias, amigos tensores. Um, on this thing I'm calling the road to Riemannian geometry, we're now on the fourth or fifth video of this, and I finally gathered up all of the stuff scattered across my channel and put it in a new playlist called Riemannian geometry. Okay, so we're going to wrap it up with finding some information about the Riemannian geometry. Now, this isn't related. This isn't necessarily related to general relativity. We're just looking at curved manifolds. Okay, so in the first one we did, we found an invariant equation for the curvature on the manifold by this equation, and the magnitude of this vector is called the Gaussian curvature. Okay. Then the second thing we did, we moved on to find the curvature of a 2D manifold, a curved manifold, and that is defined old school as the Gaussian curvature is the determinant of the second fundamental form divided by the determinant of the first fundamental form. Okay? Then we went on to find a tensor equation for the manifold. By this is called the Gaussian curvature tensor, and it's related to this thing called the shift the tensor and the partial derivative of these the normal components divided by the surface the coordinates. Okay, now up all the way till now we've been referencing a manifold embedded in a space, and let's go look at that. Okay, here is a paraboloid embedded in a three-dimensional Cartesian space. Okay, so this space is called the ambient space, and this manifold is embedded in it. So we have defined our parameterization as there's a circle that goes around here, right? We could change that circle to being larger or smaller, and we can change the angle around the circle. So that's the parameterization that we used, and we can use that information to define the basis vectors on the surface like this, right? So here's two basis vectors, and we take the product of those basis vectors, and we define a normal, which is something that sticks straight out perpendicular to these two, the basis of the vectors. So everything we've done up to date has had a reference to this normal, which is this normal now is a component of this ambient the space. Okay, so what separates the geometry we've been doing to what we're going to do is there is no longer going to be any reference to the ambient the space, and you can see why you want to do that, because as you move to higher dimensions, like in space-time, you've got 4 dimensions. What are you going to embed a 4-dimensional object in? I mean, I don't know how to ask the question. So that's the point of Riemannian geometry, is now we're going to study this curvature of this function as just relying upon the metric, the tensor. All right, there is no reference to any ambient space. So that's what it means. Okay, so we're going to, as an example, use the Riemannian curvature of a paraboloid. I'm going to use this because I got a bunch of data on it already. Okay, so here's the equation of a paraboloid, the one we just looked at. We're going to parameterize this surface with u and v. So we got these 3 parameterizations. Now we can define some surface, the basis vectors, as having a position vector with these components, okay? And just the ex, ey, and ez, the orthonormal basis for the vectors. Now, we take the derivative of that position vector with respect to u, and we get the EU basis vector. With respect to v, we get the EV basis vector, right? We've done this many, many times. Now we can define a metric, the tensor, right? So this is EU.EU, EU.EV, EV.EU, and EV.EV. Okay, then we need our inverse metric, the tensor, to do what we want to do, and it's extremely hard to get. So I went to an online matrix inverse calculator and got the answer, because it's really hard. Now we can define our Christoffel symbols. So here is the generalized equation for the Christoffel, the symbols. We've also done this many times, And the M here is the summation index, right? M upper, lower, lower, lower. Okay. So I'll pick one. I'll do one, and then I'll just give you the rest of. I'll just pick K equal U, I equal U, J equal U. Okay. So in the first case here, M is the summation index is U. In the second case, it's V. Okay. So let's see. Here is the component of the contravariant metric tensor UU. The partial, let's see, these two cancel. The partial of GUU with respect to U is 8U. Then we got our second term here. Here is this component of the metric, the tensor. This is 0 because there is no V. There is no V in GUU. This is just 4V. Let's look at that again. Yeah, okay. So that's just 4V and 4V. So that makes 8V. So we multiply. So this 2 makes that a 4. That gives us 16UV squared plus 4U minus, let's see, that 2 makes that a 2. So this is just 2 times that gives 8UV squared. These two cancel. We get 4U over this. Okay? So here are the other three. So we got 4 non-zero components of the Christoffel symbol using this parameterization. Okay, now we want to find our Riemann curvature tensor, and we've seen this bad boy. He is nasty. Okay, so I'm going to do one, and I'll give you the others. All right, so in this case, the sigma is U, alpha is U, beta is V, and gamma is U. So you fill all of this in with these. These are the free indexes. And remember, this tau, 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 tau is a summation index. So that's why there's 4 terms, right? Because this turns into 2 each. Okay, now let's get rocking. So the partial of gamma UUU with respect to V, where's gamma? Here it is. Okay, so we use the quotient rule, right? So the denominator times the derivative of the numerator. This has no V component, so that's 0, minus the numerator times derivative of the denominator divided by the denominator squared. So that's what that is. Okay? Now, anything that has a mix in it, gamma, UV here, there are no mixed ones, you see? They're all 0. So any of those, that's 0, that's 0, that's 0, and this is 0. So we only get 2 terms. And here's the product of these two, okay? So we multiply these two together, we get this. We subtract it, and here it is. Okay, so here's 1, 2, 3, 4. Now, these are components of the Riemannian tensor of the second kind, and we want the components of the first kind. And you say, why do you want that? We're going to get there. Now, how do we do that? Okay, well, we multiply what we have by the components of the metric, the tensor, where this becomes a summation index, right? So what it does is it moves this U over to here. So these components times these component yields that. Okay, and we want to do all 4 of them like this. All right, so the identities of the Riemann tensor, there's 2 important identities here of when you're dealing with the tensor components of the first kind, is if you swap these first 2 indices, you get a negative. So it's the same component but negative. If you swap the last 2 indices, you get the same component but negative. Okay? So a Riemannian manifold has n to the 4th components for the Riemann tensor, but due to these symmetries, only this equation are independent. So for a 2D surface, n equal 2, and that equation becomes 1. So there's really only one of these that will represent what we need. And if you keep swapping the indices around on the ones we've done, you will come out to find there's only one, and it is R1212, which in our case, since U is 1 and V is 2, is RUVUV. Now, this is true for any two-dimensional of the surface, not just this one, any two-dimensional of the surface. Okay? So we want to find that, but we don't have it. So we only got this one as an example. We got U, VVU. How do we turn that into RUVUV? Well, the first thing we do is lower the index. Right? So here's our equation where I is the summation index. We only got two dimensions. So in the first case, it's U. In the second case, it's V. So we get these components. So we found this, we found that, we found this, and we found that. All right. So RUU is this. This component is this. We're going to add it to this component is this. And this component is that. All right. So you crunch all that algebra and you're going to get this. So what I did here was I foiled this and I got these four terms, 1, 2, 3, 4. And 4 times 16 is 64 UV squared, so that cancels that. I factored a 4 out of here. You see these three terms are left? Factored a negative the 4 out and left this, and that takes out one of these, so it just leaves negative 4 over this, okay? But that's not the answer we want because we've got 1, 2, 2, 1. We want 1, 2, 1, 2. How do we do that? Well, that's where these identities come in. If we swap these two indices, we pick up a negative. So a negative times a negative is a positive, and we get this. And that is identical to the Gaussian curvature defined old school way, determinant of the second fundamental form divided by the determinant of the first fundamental form. You get the same answer, okay? So the actual definition, the proportionality between these two things is the Gaussian curvature is equal to the Riemann tensor divided by the determinant of the metric tensor. But now remember, we parameterized in x, y, z. So that's the metric tensor of the Cartesian space, which is the identity matrix, and the determinant is just 1. So it's just this divided by 1, which gives you the same answer. So this is the first time I've done this, and it was fun. Learning how to do this and how it relates to this. So now we're into Riemannian geometry finally. All right, thanks for watching. See you later.